Welcome to Math with Miss Swartz. I know some of you have not had a lesson actually done on one of these videos yet, and so some important things that you may need to know. I might give you a signal to pause at a few different times to write some things down. You're going to want to understand this information, obviously, and this is a little bit different than learning it when I'm up in the classroom. But the best thing is, at any time, you can come ask me questions if you don't understand something. So feel free to do that. Okay? So today's essential question is, how can we multiply and divide square roots? We're looking at property of radicals. We've looked a little bit with radicals when we were working with Pythagorean theorem and that type of stuff. And it is still very important that you know the perfect squares of 1 through 15. Okay? And I would even say 1 through 20, but because we kind of looked at some of those, but 1 through 15 is very important. So if you don't know those yet, make sure you start to get to know them. So let's get started. Okay, some general information here. Essentially what we're going to be looking at today is simplifying radicals. And a radical's expression is an expression that contains a radical. Okay, so here we go. Here's the radical. Some things you may need to know about it. The actual symbol is called a radical symbol. Okay, and then inside this n would be considered the radicand. Okay, and to have a radical in simplest form, these conditions need to be true. So no radicands can have perfect square factors other than 1. So inside my radical, this n value cannot be like 16, because we can simplify that. So it can remain if it's something like 5, because that's not a perfect square. Another condition that needs to be met, no radicands contain fractions. So something like this, we need to simplify, okay? And we'll talk about how that is. And then no radicals appear in the denominator of a fraction. So if we had something like this, we would need to work to get rid of the radical in the denominator, and we will discuss how to do that. So this might be one of those points where it's good to pause, maybe write some of these items down. All right, so the product property of square root says that the square root of a product equals the product of the square roots of the factors. So again, wording always a little more confusing than actually looking at this. If we say the square root of 9 times 5, okay, or even if we were to say the square root of 45, okay, which is the same as the square root of 9 times 5, we can separate that out to give us the square root of 9 times the square root of 5. So this helps us simplify, because then what is the square root of 9? Well, that's 3. The square root of 5 we can't simplify any further because it's not a perfect square. So this would be simplified. So the algebra says the square root of a times b would be the square root of a times the square root of b, as long as a and b are greater than 0, which brings up another good point. So can we actually have this? So I need to think about that for a second. The square root of negative 25. So think about what the square root means. When you're looking for a square root, you're looking for the number when multiplied by itself gives you that radicand. So in this case 9, the square root of 9, we're looking for what numbers multiplied by themselves give you 9. Well, that's 3 times 3. Is there any number that multiplied by itself is going to give you negative 25? So think about that. If you're thinking 5 times negative 5, well, those aren't the same numbers. Negative 5 times 5, those aren't the same numbers. Is there any number that multiplied by itself will give you negative 25? Well, negative 5 times negative 5 is just positive 25. So that is why anything under the radical needs to be positive. It's impossible for your radicand to be negative. Okay, so let's look at some examples. First, they have some where they step them out, and then we'll do some together. So if you look at A, they have the square root of 108, and they want you to simplify that. So they say factor using the greatest perfect square factor, which sometimes is hard to think about, but you can work through some of them, hopefully. So they broke it down to 36 times 3, because 36 is your greatest perfect square factor. So you just have to work through those perfect squares. So you work your way down. So then they break it down to the square root of 36 times the square root of 3, and then they break it down to 6 times the square root of 3. On B, it's a little different. It's not just a number. We have some variables involved, which we generally tend to add some variables. So we have the square root of 9x cubed, and we want to break it down using the greatest perfect square factor. Well, 9's already the greatest perfect square, so we're good there. We just have to break down our exponents. So the greatest perfect square factor would be x squared, and you could pull out times another x. So then just separate them all out, the square root of 9 times the square root of x squared times the square root of x, and simplify. Square root of 9 is 3, and the square root of x squared is x, and then we're just going to leave the square root of x by itself. Good. So from there, let's try a few together. So it's good to write these examples down. Okay, so the square root of 24. So if we think about the biggest perfect square factor, we're going to break that down to, well, if you start working through the perfect squares, the biggest perfect square you would see is 4. 4 times 6 gives us 24. So then we could break that down to the square root of 4 times the square root of 6. Well, what's the square root of 4? That's 2. And then the square root of 6 is as simplified as it can get. So this would be our simplified expression. Okay, number 2, we have a negative on the outside of the radical, which is okay. All that means is the opposite of the square root of 80. So that's fine. It just can't be inside the radical. So we'll just bring it along with us. So we need the greatest perfect square, and we're talking about 80. And sometimes, like I said, it's hard to think about. In this case, it would be 16, I believe. Make sure here. Yep. 16 times 5 gives us 80. So we could separate this out. The opposite of the square root of 16 times the square root of 5. We get the opposite of 4 times the square root of 5. And that would be simplified. Okay, we're going to do number 3. We probably won't get to number 4. But we'll look here for number 3. As you can see, 49 is already a perfect square, so I don't have to do much work there. But with the x cubed, okay, we've seen that before. So we're going to do x squared times x. So then we would have the square root of 49 times the square root of x squared, because we can separate these out, times the square root of x. So this would be 7x times the square root of x. Awesome. Okay, next part here, we have the quotient property, which is pretty much the same thing as the product property. So the square root of a quotient equals the quotient of the square roots of the numerator and the denominator. Okay, so the square root of 3/4, like we said, we can't have a fraction underneath that radical. So we're going to separate it out, square root of 3 over the square root of 4, and then simplify from there. We would have the square root of 3 over 2. Again, A needs to be greater than 0, B needs to be greater than 0. And B cannot equal 0 because we can't have that in the denominator. So some more examples here. Here we have the square root of 15 over 64. So we separated out the square root of 15 over the square root of 64, which would give us the square root of 15 over 8. Same thing here, square root of 81 over x squared, separate them out. So we'd have 9 over x. So a few more examples here. So we're just separating it out, square root of 23 over the square root of 9, which would give us the square root of 23 over 3. And then we have the opposite again. So we have the square root of 17 over the square root of 100. So the square root of 17 over 10. Here we have the square root of 36 over the square root of z to the second. So then we would have 6 over z. And here we'd have the square root of 4x squared over the square root of 64, which gives us 2x over 8, which you could simplify if you wanted. Okay, so as you can see, with all of these, we no longer have a fraction in the radical symbol, and we no longer have the square root in the denominator. So the question becomes, what happens if we still have that square root in the denominator? That's the last part of today, and I need to try to wrap it up here. So if I get going too quick, just pause the video. So when a radical is in the denominator of a fraction, we can multiply the fraction by an appropriate form of 1 to eliminate the radical from the denominator. It's called rationalizing the denominator. So what you need to understand is whenever you're multiplying something like 2 over 2, essentially you're multiplying by 1, but we might make it look a little different than 1 to help us get where we need to be, and you'll see what that means in a second. So the question here that I posed for you is, what is the square root of 9 times the square root of 9? So if you multiply those, remember we can break that apart, but we can also put it back together. Well, 9 times 9 is 81. So what is the square root of 81? Well, it's actually 9. So our understanding is if we multiply two square roots with the same thing, what we get is the radicand. Okay, this is going to help us be able to rationalize the denominator. So let's look at some examples of this. Okay, so in this case we have the square root of 5 over the square root of 3n. We've separated out the fraction possibly, but right now this is not simplified because it doesn't meet one of those conditions that we set at the beginning, that there cannot be a radical in the denominator. So what we do is we multiply by the actual denominator, but we're going to multiply by 1 essentially, because if I multiply by the same thing top and bottom, I'm multiplying by 1. So what I'm going to do is multiply by the square root of 3n over the square root of 3n. Okay, when I do this, I just need to multiply across. So the square root of 5 times the square root of 3n is going to give me the square root of 15n. 5 times 3 is 15, and then you have an n. And then multiply by the square roots here, but we kind of already talked about what that's going to look like. So we'll get there, but it does break it down. So the square root of, we get 3 times 3 is 9, and then n times n is n squared. Okay, so then continue to simplify. If you can jump from here to here, you will eventually hopefully be able to do that, and you can. So the square root of 15n, there's nothing we can do there, but we can break apart 9 and n squared. Square root of 9 is 3, and the square root of n squared is n. So really what you're thinking about, it's the same concept as multiplying the square root of 9 times the square root of 9. Because we got 9, well, the square root of 3n times the square root of 3n is 3n. So I want to do at least 2 more examples, but we're going to have to move. We're going to come back to this. Actually, we're going to do one example of this, conjugates. So conjugates, the binomials of a times b times the square root of b plus c times the square root of d, and then the same concept except subtraction, are called conjugates. We can use these to simplify radical expressions that contain a sum or a difference. So in the bottom here, we can't just multiply by negative, or the square root of 3 here. We actually have to understand that this all comes together as a package. So what we can do is multiply by its conjugate. Okay, its conjugate is going to be the same thing except a plus. So 2 plus the square root of 3 over 2 plus the square root of 3. Okay, when we do that, we get 7 times 2 plus the square root of 3 over, so now if we're multiplying this, okay, 2, essentially think of it